we're going to see this, analyze this problem because it's significant to vehicles. So can you actually see, I'm going to tell you what it is so that everybody gets interested to learn this. Because as academic exercise as it looks, is actually a very practical example. So that's why I want to show you. There we go. It says that you have a optimum hemisphere of mass m and radius r, and it's released from rest in the position that you're seeing here. Assuming that the hemisphere rolls without sliding, determine A, the angular velocity after it has rolled through 90 degrees. B, the normal reaction exerted by the surface on the hemisphere at the same instant. If you relate this to vehicle dynamics, you can see, you could actually do a small modification of this drawing, and you'll see how closely related this is. Realistic. This is as if you see you could have wheels here on this side, just like it's like the model, the perfect model of a vehicle about to roll over, to roll on its top. But the reason that I'm interested in you analyzing this is because of the value that we get. The question is, part B of the problem is asking you what is the reaction between the body and the ground when the body rotated 90 degrees. That is the question. Yeah. So in here, it's as if where the letter B and A are, they would be the wheels place. Okay. The thing that we need to consider here is determine the kinematic relation between A and B, I mean omega and B. That's easy. B says determine the kinetic energy for the positions 1 and 2 using the principle of conservation of energy. Right? The first thing we're going to do is use the principle of work and energy and determine what the work forces and the analog forces. Okay. And then we have the use of principle of work and energy, and finally determine the reaction. Okay, so take a look in here. This is a very significant one because on the, what are we doing here? This is the, like the vehicle rolls on its roof. See, this is why I think it's very important. So the vehicle obviously has a center of mass about which this body rotates. I mean, let me correct that. The body rotates about the point of contact with the ground at every instant. But the center of mass is the one that we need to consider when we apply the equations of motion. So in this case, you have the velocity is 5/8 r omega. And then we have the moment of inertia here. So determine the kinetic energy for position 1 and 2. So you have the kinetic energy 1 is 0, position 2 at 90 degrees is still rolling, right? So that's why you have these equations, this 1/2 of m b squared plus 1/2 of I omega squared. Okay, that's the complete energy. Okay. What's the work done by the external forces on this particular case? Do you see it in there? The center of mass was in half, in the middle at the point O. But when it's on its roof, or the same hemisphere is on its side, then G has come down somehow. So that is a change in potential energy that needs to be accounted. And so the work done by the external forces is mg times 38r. Now, how do we use the principle of work and energy to solve this? So you see, you have the kinetic energy plus the sum of the internal energy equals to the kinetic energy 2. So you have, this is the other equation that says that mg times 3/8 should be 33/40 times 13/40 mr squared omega squared. So omega squared is 1.74 g over L. So what we need to do is to calculate the reaction on B. The left hand side indicates the action reaction is with the normal in there, and the one on the outside is the one is on the right hand side you have mass times acceleration. So in this case, alpha is 0 because there's uniform rotation, and then the acceleration about the point O is the acceleration is 0. Then if we equate the summation of the forces equals forces in the y direction is equal to the summation of the forces in this effective forces. So that would be n minus mg equals m38 rw squared. Other one is mg plus 3/8 times r times 0.174 times gr This is the what is significant here is that the normal is 1.43 the weight of the car. That's the entire reason why I wanted to talk to you about this. The question that you should ask in your mind as engineers is 1.3 times the weight of the car enough? The law, the way it is, right now, the way in practice they use 1.5 for American cars. Well, we can do a drop test on a vehicle and see that this load, dropping it from even from 1 foot, would exceed this value. So that's why I wanted to show you this, because it is a simple example of a roll on its top with very slow roll, yet it produces a reaction that is 1.43 times the weight of the car, much higher than the weight of the car. So that gives us an idea that how to design the roof. And I know that the Volvo, the SX90, has been tested at 90 miles an hour and no collapse of the roof. Amazing car, huh? But other cars, they just kept falling on those drop tests and just the roof collapsed as a pancake. So it is important to know. I wanted you to know that we have a standard that in fact is way too low compared to the European cars. Mercedes and BMWs have much higher um, values of this of this number that relates the weight of the car to the reaction on the ground. Okay. Let's stop now.